Hi, I'm Rober Virding. I work for Erlang Solutions. I am sometimes called Principal Language Expert. I think I've been called Senior Architect as well too. I don't really know what that is, but that's me. So this talk's called the Hitchhiker Tour of the VM, and just a quick tour of the VM, the Erlang VM, and looking at some of the features of it and how it affects your programs and how you can sometimes use it to make your systems run better. Is the microphone working? Yes. Right. Okay. So yeah. So the first question, of course, is what is the VM? It's a number of things. I mean, it's a virtual machine to run Erlang. So when you compile Erlang, you compile it down to a virtual, compile down to an assembler for a virtual machine, and the VM is the system which runs those instructions. It also contains interfaces to the outside world. It's very well to run your Erlang program, but to do something you have to communicate to the outside world. So it contains basically the ports to talk in the outside world, and the nifs to call C functions as well. It implements those. And it also has a bunch of built-in useful functions. So not just things, these aren't things written in Erlang, but just things below all this that are necessary or useful to be able to run your code. Some of these functions are part of the Erlang language, like spawn or link, and some of their just useful library stuff you couldn't do efficiently in Erlang, or need to access the operating system or something like this. Today, many of these could if they'd been written today, they would have been replaced using nifs instead. Back in the old days, before nifs we could. I'm not going to run through Erlang. I'm assuming everyone here at this level knows it. But there are a few properties of the Erlang system which are very important when you're implementing it. So this is not the language itself, it's the system. So the VM or any implementation of Erlang needs to support lightweight massive concurrency. So it is assumed you can create basically as many processes as you need. Literally millions of them used. You need fast, lightweight, asynchronous communication. The language has that, the system has to support it. You need process isolation and you need primitives for doing error handling. And you need support for doing code upgrades, and the whole thing has to be soft real time. What that more or less means in this case is that you shouldn't notice things going on in the system. So if the system makes pauses, which it does to do things, you shouldn't notice that. That's the soft part of the soft real time. So Erlang has concept of time, but it's not hard real time. So these are properties of the system itself. Then you have a bunch of language properties. Things like immutable data, pattern matching, it's a functional language. They're important, but they're not rocket science in this thing. So these things, this part of the language, you'll find in a lot of other functional languages as well. So the system has to handle that, but it's nothing really special in that sense. For example, the pattern matching. There's a pattern matching compiler in the compiler. That's basically standard fare how to do that. But it's there. So I'm not going to really talk about that at all. So, to run Erlang, the VM needs to support all this. And the difficult bit is not the sequential parts, it's not the functional language specific parts, it's the other things, it's the first thing. So we're going to look at the concept of schedulers, processes, memory management, with that mentioned parsing multi-core as well. And time does not allow us to get very deep into this one, unfortunately. There's an awful lot you can say about this, so we'll just be looking at a quick overview. So, the first thing we'll start looking at is the concept of schedulers. So, when you're running an Erlang system, or running a VM, you're running a number of schedulers. And they are more or less semi-autonomous Erlang schedulers. So each scheduler runs as much as possible, it runs by itself. It tries not to interact with the outside world or other schedulers more than necessary. They have to, of course. And each scheduler runs in its own VM thread. So each one is a separate thread and it's running in a normal VM thread. It does all its own stuff, so it contains its own run queue. So each of the schedulers knows exactly what it's supposed to be doing. It has its own run queue to run things. And the run queue is not just Erlang processes, it's other things that the VM has to take care of. So if for some reason the VM, or the scheduler, has to do something, the thing it will have to do will be put on the run queue and it can process it when it gets there. So there are very few things like doing interrupts or something like this in each schedule. This makes many things much easier. Seeing when the VM plucks the next thing off the run queue to do something, it will be in a known state, it will have everything set up in the right way so it can do things. So many things will be put on there. And each scheduler, as I said, tries to run as separately as possible. So what you want to try and do in any multi-core SMP system is to try and reduce synchronization of locks. Synchronization of locks are nasty stuff. They cost a lot to do that. And unfortunately, the more concurrency or parallelism you get in your system, the more that will cost you. So trying to reduce this as much as possible is always a big win. And the OTP group put a lot of effort into trying to reduce locks in the system. There are still locks in there, but they're getting rid of them as fast as they can. So for example, so now the sending a message actually doesn't do a lock in the system, even if the process you're sending to happens to be running on another thread, another schedule. It doesn't have to lock it. We've got to send the message down actually to 2 writes in the system. And it's a big win. I've got an example I can show at the very end of just how much locking and synchronization actually can cost. So we have the schedulers, their own little VM, they're running on a thread. By default, you'll get 1 thread per core. You can specify when you start the Erlang VM how many threads you want running, how many support you want running. Generally, you don't want to run more of the Erlang scheduler threads than there are cores. That really doesn't give you anything. Sometimes, however, you do want to run fewer schedulers than there are cores. Your machine is doing something else. You might want to tell Erlang, don't try and run on everything. Don't try and hog as much of the machine as possible. By default, Erlang will grab everything you can and use that. You might want to say, yeah, I'm running something else over a database system. I just don't want to run Erlang on my 8 cores. I'll run Erlang on 5 cores or 3 cores. You can do that from the start of it. So that's a perfectly valid reason not to let Erlang. So we start up Erlang, it runs all our schedulers. They're all running more or less separately, as much more separate as they can be. Of course, they'll get different load. Some things running on one schedule will take a lot of time, other things running on another schedule won't, or they'll just be blocking and suspending and things like this. So there's a built-in mechanism in the schedulers for balancing, for load balancing. So what happens here, every period, it's somewhere around 20 to 40,000 reductions. The reduction in the Erlang point of Erlang sense is a function, basically an Erlang function. So there's still call reductions way back in the old days when it was implemented in Prolog, and Prolog doesn't do function calls, they do reductions. So that's where the word comes from. But today, basically it means Erlang function call. So every about 20 to 40,000 function calls, one of the schedules will be chosen to be master. And that's generally the first scheduler that reaches this count. It says, I'm here, then it tells all the other schedulers, I'm now the master. And what it then does is, it goes out and looks at all the schedulers, tries to quickly work out how balanced is the system. Is it so that the run queue on one schedule is very long and other schedulers are very short, or something like this, and it just tries to balance the system. So in this sense, the system is self-balancing. And I've just tried to balance the workloads and optimize the system. And it does this by putting things on run queues. So it can tell a scheduler, move this process from you to someone else. Or the other way, it can tell the scheduler, grab a process from this scheduler and put it on your run queue. And it puts this type of information onto the run queue of the very schedule. And so they can keep on working and they'll process this information when it gets their turn on the run queues. A lot of things end up. So that means the system is more or less self-balancing in these periods. And after the master's done this, everything just keeps on working until the next time after the next 20 or 40k productions. I can't remember exactly, it was 20 or 40k, somewhere around there. A new master's chosen, which then does rescheduling again and it keeps on going. So here's a time when the schedules are actually interacting with each other. But none of them are suspended for this. So just because someone is doing balancing doesn't mean the other scheduler will then suspend and sit and wait for this. So there's no suspension going on. All the master's doing is just putting sort of commands onto the run queues of the other schedulers while they're working. There's no sort of central synchronization for this. Any form of central synchronization is avoided as much as possible. There's actually I know of one case where we done. So that's basically the concept of schedulers and the basic concept of balancing, how this works. So now we're running inside our schedulers, and they have their processes, they have their own run queues and they're doing. And on the run queue, of course, will be Erlang processes that need to be run. And processes are scheduled for different, processes are suspended for different reasons. So when a process is waiting for a message, it becomes suspended. So it's not on the run queue, it's not running, it's suspended and sits and waits until someone sends it a message. So having a process waiting for a message is not a busy wait, it just sits there. Which also means that it doesn't cost anything in the CPU to have lots of processes which aren't doing anything, just sitting waiting for messages. So for example, having supervisors. Hopefully a supervisor never does anything. It should start its process and just sit and wait until it's told to die and then kill all the processes. And that doesn't cost anything. It doesn't cost any CPU time to do this. The process just sitting there, it's not a busy wait, it's just waiting. And it doesn't become runnable, it's not put on the run queue until a message actually arrives at it. Then it's put on the run queue when its turn comes, it will process that message. Processes that are running, what have I written there? Will not schedule by. That doesn't seem right. Anyway, so they will be unscheduled or removed or put from running for two reasons. Either they do a receive and there's no message which matches, in which case they'll be suspended, or after 2,000 reductions, a process will be rescheduled. So no process, Erlang process is allowed to block the system. So even if a process is continually running, after 2,000 function calls, it'll just be removed, the work will be suspended and just rescheduled for the end of the run queue. So nothing will block. I've heard they're thinking of increasing this level of 2,000 productions, seeing everything going much faster these days. That's a very short amount of time. So this is just a simple use of the run queues, and meaning that no process waiting for messages doesn't cost anything, and no process is allowed to block the system. So they'll be rescheduled. A bit about memory. Basically, there are 4 different types of memory areas, memory types in the system. So there are process heaps. Each process has its own heap. X tables, they're in a separate area as well. They're outside all processes in a separate area. The atom table is also its own separate area for keeping atoms. And we've got, I think it's called the large binary space, where we put big binaries. start off, the atom table is the easiest. So when you create an atom, it's in turn in a global atom table. Which means comparison of atoms really fast. So all an atom is in data is just an index into the atom table, so you can compare atoms very fast. Which means there's no need to not use an atom. Say, I want a tag of some sort. There's no need to not use an atom. Say, replacing with an integer. Just a tag that. It won't go faster. So I can happily use OK instead of, say, returning 1 or 0 or something like this. It won't make any difference. But, atoms are never deleted. So once you create an atom, it's always there. It's global, it's always there. And they're not garbage collected at all. So you should be careful with programs that create atoms. This is generally not a problem with code. I mean, even if you have a lot of atoms in code, there really aren't that many. There's not as many as you would think. I think the atom table by default is a million atoms or something like this, and you will not fill it by code. So that's not a problem. But you should avoid doing programs that create atoms on the fly, because then you will fill the atom table. And when that happens, the system crashes. There is just no way out. If you've got a million slots in the atom table and you try to create the 1,000,001th atom, the system crashes. The whole system, bang, goes down. So avoid applications where you create atoms. There is some help, because you have the basic functions to create atoms, list to atom and binding to atom. There's also functions called list to existing atom and binding to existing atom, which will only create the atom if it already exists. So it's a way of allowing you to make sure you don't create new unknown atoms. So a typical case you should avoid is you're getting some message into the outside world, and you're parsing that, and building an Erlang representation of that, and you're creating atoms on the fly without really checking what you're doing. That is a typical case that will eventually crash. It also leaves you very open for attack. The typical attack is just send things in, fill the atom table and crash the system. Yes?
Are atoms created in compile time?
Yeah. They're created in compile time. And when you load a module in, there'll be a number of atoms in the module. They'll be created. But you cannot fill the atom table with code.
So you don't need to initialize?
No, you don't have to initialize anything, no. It's all done automatically. It's all the atoms that are created. Avoid creating atoms. So that's the atom table. Another area is what I call the large binary space. So generally all data is local to the process on the process heap, but binaries that are bigger than 64 bytes aren't. So they're put in a separate area, and so you can send them very efficiently with just send them once, which is very nice if you're processing large binaries. So you can have a system that sends large binaries through the system without actually the minimum amount of copy of the binary. Because only the quantities. And that can save a lot of memory. I mean, if you're passing a big binary through 10 processes, you don't have to make 10 copies of it. But one interesting thing about all these decisions is that there's usually no best choice. So whatever choice you make, someone's going to win from it, and someone's going to say this is terrible. So whatever you're doing, like with the atoms, we could have not a global atom table, just have atoms as objects, which would be very fine because we wouldn't have to be garbage collected, but then atom comparison would be much slower. Such a choice, yes.
Can you explicitly call garbage collection?
You can explicitly call yes, but it won't garbage collect the atom table. And the trouble with a large binary space is that it's reference counted. So every time a process accesses one of these binaries, the reference count of the binaries is increased for every process that has reference to the binary. Which means the binary can't be removed, which means until all the processes that have sort of seen this binary have been garbage collected and their reference count decremented, saying, well, I'm no longer referencing this binary. And that can take a long time. So a real problem is that you just get too many large binaries in the system too quickly, and the garbage collector in the system can't keep up. And I saw a very simple example of this last week. A guy had written, just doing a small benchmark program. So he had two Outline nodes talking to each other, and on one node he created a 1 megabyte binary. And then he started up, I think, 2,000 processes on that, sending that binary across to the other node to 2,000 processes on the other node. Just sending the same binary across. And after a short time, node 2, the one receiving all the messages, crashed because it was overflowing the binary space. Because every time that binary was sent, okay, there's only one copy on the sending node, but on the receiving node, a new copy was made for every time the binary arrived. And all the processes were doing receiving it, were just sitting in a loop receiving the message. So they basically did no garbage collection at all, and that would just result in the binary space overflowing and the system crashing. And also it was actually running on a Mac, so you got a bus error when they were doing the crash dumps. It didn't get any crash dump either. The worst of all cases. The system crashed, you couldn't find out why. And that was just the binary space filling up so quickly because there was no garbage collection done at all. And calling the garbage collector actually helped that solve the problem, but it slowed down the program. Most people do not have a problem with this one. So there are a few applications that do. It's just something to be aware of. Again, it's a downside. Having large binary space means you don't have to copy large binary space. Sending messages is much more efficient, but you pay for it and you might get noticed. It's the same thing with X tables. So data in X tables is not in your processing. It says this somewhere. And it's not implicitly garbage collected. So it's not like normal data would just happen with the garbage collector will be playing when no one accesses it. When you delete an object, when you delete a table or an element of the table, of course, that data will then be reclaimed and be able to be reused. But the table itself won't be garbage collected just because no one references it. And it also means that every time you access an element in that table, you're copying data backwards and forwards between the process and the end table. So when you write something in the end table, you're copying it into the end table. When you're accessing data, you're reading it back in. That's one reason for having the functions like match and select, because you can do more complex selecting of data without actually having to copy it into your process. That saves you effort. But there's one very big benefit, or two big benefits from using N tables. One is you can store large amounts of data. Gigabytes is definitely possible, done. Right? You can have N tables which are 10 gigabytes big, 100 gigabytes of data, which would be totally unreasonable to store in a processor. Single moment wide. So that's one very good reason to use N tables, is you can do this. There are applications that do it. Another is it makes it easy to share data. You can have multiple processors accessing the same X table, which means they don't have to talk to a process to do this. The downside is the X table is not a database, it's just a raw data store with very limited transactions. So there's no transaction handling at all in the X table. There are reasons for doing that. Also, the lookup time in an X table is faster. Using normal hash X table sets type, it's very fast lookup. Faster than you could write yourself, keeping data in the process. But again, it depends what you want to do, how you're accessing it. If I've only got 10 elements, I'm just doing locally to a process, it's probably much more efficient just to keep that in the list locally to the process and search through it. But it's there. There's some things that are definitely the right solution. Be aware of it. The fourth area is processing. So each process has a separate heap in the thing. And all process data is local to a process. That's in the heap. So there's no shared data between processes. Any sharing is done by things like putting data in X tables or the large binaries or something. So there's no shared memory at all, or shared data at all between processes. So that means also that sending messages means copying data. When you send a message from one process to another, you are copying the message to that other process. That's it. That is actually not required by Erlang. Erlang doesn't say anything about how I send a message to a process. All it says is that the process have to be isolated, so that one process can happily crash and not ruin the memory for anyone else. Having separate heaps and copying is one implementation. You can do other ways as well. Seeing data is immutable, you can actually share data between processes. If the implementation can share data, you don't notice it. You can. There are ways of setting the minimum process heap size. We'll see some more about that as well, which you can have some benefits on. Go through that. Then the question arises, of course, all this copying of data, isn't it very inefficient? Isn't this an extremely inefficient way of doing message passing? Why have to copy everything? Why not just share data and share send references? Well, in one sense it is, right? But again, with everything else, it's sort of, like maybe it's inefficient. But having separate process heaps gives you a lot of benefits as well. Yes, I have to copy data, but it gives me a lot of other benefits as well. So it allows you, well, the beam, to garbage collect every process separately. And most generally process heaps are pretty small. If you look at them. Maybe a few processes that grow, but generally they're pretty small. It also means that as it garbage collects each process, the system by process, per process, it means I can run a simple garbage collector on just the process, and I don't have to worry about blocking the system. So it makes the garbage collector much more efficient. I basically do a stop and garbage collect per process, and that makes the garbage collector much more efficient to do that. It also becomes simpler, which is not something to be scorned, right? The trouble with writing memory management systems like garbage collectors is that when you have an error in them, you see the result of the error much later. A couple of garbage collectors later, you find that the system finds that some point is all wrong and the whole thing crashes. You have absolutely no idea what it was. So having a simpler garbage collector, having a garbage collector that's simpler is a big win. And if you had a shared heap, it's not. The technology is there to use this to do, say, shared heap garbage collectors and do them incrementally in such a way that you don't notice the pauses. They become more complex and they become less efficient. Less efficient in the sense that they're doing more work than they would need to do if they could stop and copy. And I've done some old ones before on single cores. It's just more work. The garbage collector just takes more time because it's doing more work than it needs to be if it could stop and copy. Basically, it's taking a snapshot of the system as it was before and working on that while the system is being modified, which means it's both garbage collecting things as they were before and garbage collecting things as they are now. And if you're doing it on an SMP or a multi-core system, of course, then you need synchronization. You cannot go out and fiddle with a heap while other threads are mutating the heap. So then you need synchronization. Synchronization costs. We have to work out systems to get around the synchronization. So, for example, the standard JVM, it has a parallel garbage collector. I think they're called concurrent collector. I can't remember the name now. That basically says if you're running on multiple threads, you will say one thread will do garbage collection, the other threads will do work. Which is nice, but it requires synchronization. So, for every pass of the time it's collected run, it needs 2 synchronization times. So all threads just basically have to run, synchronize, and then keep on going and then synchronize again. The second synchronization time can actually take quite a while. So yes, you're running the collected parallel, but you're paying for it by having to do synchronization. The garbage collector with the copying collector, that's pretty standard. It's just generally one copying instead of marks is generally more efficient instead of mark sweep. If most of your data is, or a very small portion of your data is live. then you only look at that for one day. It's a generational collector, which is very good for this type of thing. Generational collectors are based on the heuristics that most data you create will die very quickly. So if I just try to be optimized against the case of the new data, most of it will be dead and wrong very quickly. And that's generally true of languages type Erlang. We have immutable data and always creating new data, mutating data. So there's two spaces. There's a new area for new data, and eventually data will be copied over to the old space where the old data is. And after a number of collections of new data, we say, okay, now this data's been around so long, so we'll say it's going to last a long time. We'll move across the old data space. Hopefully, not much will end up in the old data. Hopefully, most will die quickly, so we'll get rid of it. Eventually, you'll fill up the old heap, then you have to garbage collect it. Then you just have to do the whole process, and you can't do the generational schemes. Generations are generally much faster. So you have to do what's called a full sweep load. This is just standard. So it's very nice being able to do that. And seeing we're doing it, we're stopping in garbage collecting every process. This is much easier to do when you do these type of functionalities. Which is very nice. You can do there's some simple tuning of process heaps. So you can set a minimum process heap size. By default, the heap starts out very small. And for an Erlang process, everything's on the heap, both the process stack and the process data on the heap. And it's somewhere around 200 to 300 words, I think, is the minimum size. The default minimum size of the process heap. That truly means you can have a lot of processes. Most processes don't grow very big, and you can have a lot of processes. You can set the minimum size. That has some uses. It means that if I know my process is going to be quite big, I can start off being big and it'll grow more efficiently. So I have to do a lot of garbage collections on the way, which is stuff. But it will never get smaller than the size I set. So I have to be slightly careful. Yeah, I know, I'm running out of time. I've run out of time. Oh, we're all out of time. Anyway, yeah, so it will never shrink below that size. So though I might be tempted to make every process big, they'll just fill my system. So I don't want to do that. But you can selectively do it. If you know, for example, this process is going to grow, I can set the process size quite big at the beginning and it'll be more efficient. Another thing you can do, if you know what's going on in your system, I can say, okay, this process is going to be short-lived. If I make the heap big enough so it never has to garbage collect in its time, when I create this process, I will suddenly make it go faster, more efficient. So I can create the process big. I can say, yeah, I'm going to need 1.5 megabytes of data for this process. I know that, so I'll create that at the beginning. When the process dies, now it has to do garbage collection. Of course, if I'm wrong, I pay the price for it. Setting it, you can set it globally and per process. Another thing you can do is just control garbage collection, the generational side of the garbage. So I can say after how many generational calls I want to do my course. And if that actually helps your system, not, that's black magic. You set it, you test it and see what happens. If it goes faster, it goes slower. If you get it right, your system will go faster. If you get it wrong, your system will go slower. Just test it. Sorry, I cannot give you. There's no way of working out.
Is it stable? If you're going to write today, it's going to write tomorrow.
As long as your system is stable, yes. Of course, if you go change your system along the way, that might affect it. Now, generally, write your system until you're happy. Then if you need to be, you start fiddling with things like this. Same thing with the minimum size. But if you set the full sweep after its account to a very small, like 0 or 1, you will force faster garbage collection. You will force the garbage collector to do more work, but it will collect more unused data. So you will generally use less memory in your system. So you pay the price because the garbage will do more garbage collection, it will cost you more CPU, but you will use less memory. And it has the benefit that if you do this in all your processes, you will be able to reclaim the large binary space quicker, because you're forcing each process to do full garbage collection, and it can detect if the binary is no longer used. So again, it's a balance. you win something based on. I just got one more feature than we're done. Two. A simple one, which is actually easy to use, is the async thread. And if you look in the documentation, it sets you very well how you can set this. There's a +A option when you start Erlang. It doesn't really say what it is. And what happens is that when you're doing file I/O in Erlang, file I/O of course takes time. Compared to everything else, it takes time. It's milliseconds to compared to microseconds, right? Do another step. And while you're doing file I/O, it will block that schedule. That schedule will go out and do a file access and sit and wait for the result, and then return your result back to you. That's not good if you're doing a lot of file I/O. You'll notice that in the system. So what you can do is that you can set async threads and say, I want the system to create this many threads it's going to use for file I/O. And then the I/O operations will be sent out to the asynchronous threads instead. And they won't block the scheduler. Yes, it'll still block the process doing the I/O, but the scheduler won't be blocked, and it can do other things while it's waiting for the I/O operation to complete. So I won't notice in my process as longer, but I'll be open to other things in the system, on the systems, while I'm doing I/O in the system. And typically, I mean, if you're just not doing much file I/O, it won't give you much. If you're doing a lot of file I/O, it can give you a lot. And if I just create, I have to do this when I start the system. If I do that, then the file I/O will automatically use it. Also, if I'm writing LinkedIn port drivers, so I'm using ports and writing my own LinkedIn drivers, they're there to use in my own LinkedIn drivers. So if my driver can detect they're there, I can actually use those as well for doing my own work. I can't create them when the system is running. It's something I have to do when I start it. And just a quick point here is the iNet driver never uses it. The iNet driver works completely differently. It's got different sides and file stuff. But it's a very nice feature if you're doing a lot of file I/O. I think someone told me that React starts 1,024 of these async threads because it does a lot of file I/O. Someone maybe from Basher can either confirm or tell me I'm wrong there. Yeah, we end up with two things. How to crash the beam. It's always nice to know. I'm fed up with the system. Fill the atom table. That's a surefire. When I fill the atom table and the system crashes, I cannot do anything about that. I can overflow the binary space, which is, I'm cautious, very easy. If a process heap grows too fast, the system will run out of memory and crash as well. So I can do that. A couple of nice ways of doing that is infinite recursion. That's a good way of crashing the process. Do very long message queues. So if I flood a process with more messages than it can handle, eventually the system will run out of memory and crash. That's a good typically log processing. Or I just have a lot of data in a process. I have a big heap that just grows very big, so the next time it needs to do a garbage collect, there's just not enough memory for it to do that. That's not it. And the best way, actually, is if you're writing your own nifs or LinkedIn drivers, you can narrow them. If you get a segment violation or something like this in your nif, that code is not protected at all by the Erlang system. So if you get an error in your nif, the whole system goes down. I mean, if you come from Erlang and I happily divide by 0 and I just crash my process, the Erlang system runs, I do a divide by 0 in my nif, the whole Erlang system crashes. I just want to step past this. Just show you this. The problem of synchronization. So this is a simple little program, it's called Parallel. And here we see along the bottom is the number of schedulers, along the left is this time taken to run this little demo process. Applications. And you see here, the more schedulers I add, it's taking longer time to run my application. It's using this parallelism. It's a very simple thing, but it's just taking longer time. Until somewhere around 8 it hits a level, then it evens off for a while, and then it's increasing. So if I look at the table from the speed up point of view, it's getting slower the more cores I add. The more parallel I make my system, the slower my application is moving up. And the reason, well, it's a very simple little application, just a demo system here. It spawns processes, and each process calls Erlang colon now to create timestamps. Then it just checks that all these timestamps are in order, and just returns back to its master process saying, yes, everything's fine. So if you start a few thousand of these, they'll happily spread out in all the cores. The problem is the Erlang now call. That synchronizes. Because it's guaranteed that every call you make to Erlang now will be bigger than the last one. Even if the time is the same, it's guaranteed it'll bump the count. So calls to Erlang now synchronize. And what's causing this problem is the synchronization. So synchronization is a real problem. So any effort you can make sure that your system can cut down synchronization. In the case of the VM, to cut down synchronization is a big win. That's why they're putting a lot of effort into cutting down locks and synchronization, because it really does cost you. This is not what you would expect from an application. I put more cores in, it should go faster. I put more cores in, it actually gets slower, which is not really what I expect. It's just synchronization. It's not a bad implementation now. It's just because the way now is defined, you get all the synchronization. Back when we defined it 20 years ago, we didn't have that problem because we didn't have multi-cores and SMP systems anyway, so it seemed like a good idea. Now it comes back against you. Replacing this by calling OS colons to timestamp makes it behave as it should. So if you flip it, you'll get speed ups, you'll get the right timestamp. When you get more cores, more schedulers, because you don't have the synchronization. Okay, thank you.